We went to the moon. Humans stood on another world. They walked there, then came home. Safe, alive, 6 different times. So naturally, people assume something. Mars should be the next step. Same idea, same technology, just a little farther, little more fuel, little more food, longer journey, but basically the same problem. That intuition feels reasonable. Unfortunately, it is wrong. Very wrong, in fact. Because the moon and Mars are not simply different distances. They are different problems, different physics, different constraints. And the difference lives inside one simple equation. An equation every rocket obeys. An equation discovered by Konstantin Tsiolkovsky more than a century ago. This equation is merciless. It does not care about ambition. It does not care about inspiration. It only cares about numbers. To understand Mars, we start here. First question, what does a rocket do? Not complicated, actually. A rocket throws mass backward. Hot gas shoots outward, and the rocket moves forward. Simple physics, really. Newton's third law. Push something one direction, you move the other direction. Every rocket ever built works exactly this way. But there is a catch, a cruel one. The fuel you burn later, you must carry first. And fuel has mass. Mass means weight. Weight means inertia. So the rocket becomes heavier. A heavier rocket needs more fuel, but that fuel also weighs something. So now you need more fuel to carry that fuel. And suddenly you notice something. Fuel is required to carry fuel, which means even more fuel. And the cycle keeps growing. Engineers know this spiral well. It is captured perfectly in a single equation. Delta V equals VE ln of m sub O over m sub F. At first glance, it looks harmless, but hidden inside is a brutal truth. Fuel requirements grow exponentially, not linearly. That word changes everything. Exponential growth runs away quickly. Double the speed does not mean double the fuel. It means much more fuel. 3 times speed becomes absurd. Soon, the rocket is almost fuel. Very little payload remains. This is why rockets look strange. They are mostly fuel tanks, with a tiny capsule on top. Take the legendary Saturn V, the rocket that carried humans to the moon. It weighed millions of kilograms, standing upright, towering above the launch pad. But the part that returned home was tiny. A small capsule for 3 astronauts, less than 1% of the total mass. Everything else was fuel. Fuel tanks, engines, and structures to hold fuel. Engineers solved this problem using staging. Burn a stage, then discard the empty tank. Throw it away. Become lighter. Burn another stage, and repeat again. It works, but only barely. Even with staging, the limits remain. This is what engineers call the tyranny of the rocket equation. It dominates every mission. Now think about Mars. The hardest part is launch. Leaving Earth requires speed, roughly 9.5 kilometers every second, just to reach low Earth orbit. That alone is enormous. But once in orbit, things become easier. From orbit to the moon requires much less energy, and the moon helps you. Its gravity is weak, only 1/6 of Earth's gravity, and the moon has no atmosphere, no drag, no heating during landing, and leaving the moon requires only 2.4 kilometers every second.
which means less fuel. Engineers designed the lunar module specifically for this environment, a fragile machine, extremely lightweight. When astronauts left the moon, they abandoned half the vehicle. The lower stage remained behind. The upper cabin lifted off. 2 people inside, barely enough structure to survive the ascent. They met the command module in lunar orbit, transferred crews, then abandoned that vehicle too. Everything discarded once finished. Every kilogram was precious, and after all that, the mission barely worked. The lunar mission required about 16 kilometers total velocity change, and the Saturn V was just powerful enough, just enough. Now people ask, if we did the moon, why not Mars?
That question sounds logical, but physics says otherwise, because Mars introduces new problems, bigger problems, problems the moon never had. Distance is the first one. The moon is nearby, 3 days of travel. If something fails, you can return. That actually happened during Apollo 13 mission. The spacecraft circled the moon, then came home. Mars is different. Mars is months away, 8 to 9 months each direction. Once the journey begins, there is no turning back. You are committed to the trajectory. No rescue ships, no quick return. Just empty space for months. And that is only the beginning of the problem, because Mars has something even more dangerous, an atmosphere that barely exists, thin enough to ignore, but thick enough to burn you. And that creates a nightmare engineering-wise. Landing there is far harder than landing on the moon, and that is where the real Mars problem begins. Now imagine approaching Mars after months in deep space. Your spacecraft finally arrives. A small red world fills the window. It looks calm, almost peaceful, but appearances are misleading because Mars has an atmosphere. Not a useful one, but a dangerous one. It is extremely thin, roughly 1% of Earth's atmosphere. Too thin for parachutes alone, too thick to ignore entirely. This strange middle ground creates serious trouble. When a spacecraft enters Mars' atmosphere, it arrives very fast, about 6 kilometers per second. That's 20,000 kilometers per hour. At those speeds, the air compresses. Compression heats the surrounding gas. Temperatures rise thousands of degrees. Without protection, the spacecraft burns. So engineers add heat shields, large, heavy heat shields. They absorb heat, protect the craft. But shields only solve part of the problem. After the heating comes slowing down. On Earth, this is easy. Our atmosphere is thick. Parachutes work beautifully here. They slow vehicles very effectively. But Mars refuses cooperation. Its air is too thin. Parachutes barely work, not strong enough to slow heavy vehicles, which means rockets must help. Retro rockets fire downward, burning fuel during landing. But rockets require propellant, and propellant means mass. Extra mass means more fuel during launch from Earth, which again feeds the tyranny of the rocket equation. Every solution adds weight. Every kilogram punishes you. This is why Mars landing is called the hardest problem in robotic space exploration. NASA engineers have a nickname. They call it 7 minutes of terror, because during entry, everything happens fast. There is no human control. Signals between Earth and Mars take about 20 minutes. So when landing begins, the spacecraft must decide everything itself. Guidance, navigation, engine firing, parachute deployment, all automatic, all irreversible. If anything fails, the mission ends. This already happened many times. Mars has destroyed numerous spacecraft, entire missions lost silently. Yet robotic probes are small, usually 1 ton or less. Humans require something different. A human mission needs cargo, food supplies, life support systems, radiation shielding, habitats, surface vehicles, scientific equipment. Altogether, the landing mass could reach 30 or 40 tons, and landing 40 tons on Mars has never happened, not even close. The heaviest rover ever delivered was carried by the famous Perseverance rover. Even that rover weighed just over 1 ton. To land it safely, engineers invented a bizarre machine. They called it the Sky Crane. A hovering rocket lowered the rover on cables, like a construction crane in space. Then the crane flew away and crashed far away. It worked, but scaling that idea to 40 tons is extremely difficult. And remember something important. Landing is only half the Mars mission. Astronauts must also return, and that is a completely new challenge. Because rockets need fuel, lots of fuel, and Mars has none. No gasoline stations, no rocket depots.
Nothing waiting for you, which means one option. Bring return fuel from Earth. But that idea breaks quickly. Let us imagine a simple spacecraft, 10 tons empty mass, just structure, engines, and crew cabin. To escape Mars gravity, you need about 6 kilometers per second of velocity change. Using ordinary chemical rockets, the rocket equation demands huge fuel loads. Instead of 10 tons, you might require 40 tons of propellant. 40 tons sitting on the surface of Mars. But remember how it arrived. That 40 tons had to land, which means even more mass was launched from Earth, which again demands an even larger launch rocket. And soon the numbers explode. Payload mass shrinks dramatically. Fuel mass dominates everything. This is exactly why engineers search for another idea, a clever trick to escape the tyranny of the rocket equation. Instead of bringing fuel from Earth, they propose something different. Make fuel on Mars. Use local materials to manufacture rocket propellant. This idea is called in situ resource utilization, or simply ISRU. Fortunately, Mars provides one useful ingredient: carbon dioxide. The Martian atmosphere is mostly carbon dioxide gas, about 95%, and with the right chemistry, carbon dioxide can become rocket fuel. Using hydrogen brought from Earth, a chemical reaction produces methane. Methane burns cleanly, perfect fuel for rocket engines. In fact, modern rockets, like those built by SpaceX, are already designed to use methane, which means a Mars mission might work like this. First, send robots. Robotic factories land on Mars. They begin making fuel, slowly, month after month, storing methane inside tanks, perhaps for 2 full years. Only after fuel tanks are completely full do astronauts launch from Earth. They travel to Mars, land there, explore the surface, and eventually use that fuel to return home. But this plan contains one terrifying risk. If the factory fails early, no fuel is produced. And if astronauts arrive anyway, they are stranded permanently. No fuel means no return, which is why Mars exploration demands patience, engineering, and extraordinary reliability. Because once humans step onto Mars, their survival depends entirely on machines built years earlier, machines operating alone on another planet. Let us step back for a moment. Forget engineering details briefly. Think about the entire mission. A human journey to Mars is not a quick visit. It is closer to an expedition, a very long expedition. The total mission duration could reach 3 years, roughly 36 months. 9 months travel outward, more than a year waiting, then another 9 months coming home. And during those years, astronauts live inside a very small spacecraft, no gravity most of the time, floating constantly in microgravity. Human bodies do not enjoy that. Muscles weaken slowly, bones lose calcium density.
Astronauts aboard the famous International Space Station exercise daily to slow these effects. Even then, the body changes. Now imagine 3 years in that environment. The physiological challenge alone is enormous. But space adds more dangers. Radiation is one. Earth protects us naturally. Our planet has a strong magnetic field. It deflects charged particles from the sun, and the atmosphere absorbs many cosmic rays. But once astronauts leave Earth orbit, that protection disappears. Deep space is filled with energetic radiation, particles moving near light speed. Over months, they accumulate inside human tissue, damaging DNA, increasing cancer risk dramatically. Engineers can add shielding, but shielding adds mass, and mass means fuel. Again, the rocket equation waits patiently in the background. Another difficulty is communication. Mars is very far away. Radio signals travel at the speed of light.
Even so, distance matters. Messages between Earth and Mars take time, sometimes 20 minutes, one direction, which means 40 minutes for a simple conversation. Astronauts ask a question, 40 minutes later an answer arrives. Real-time help is impossible. Explorers must solve problems completely alone, just like early sailors crossing unknown oceans. And equipment must survive for years without repair from Earth. Every pump, every valve, every circuit, everything must work perfectly, or astronauts must fix it with the tools they brought, because spare parts are limited and rescue missions do not exist. This is why engineers say Mars exploration is not just a mission, it is an entire system. Launch vehicles, orbital assembly, interplanetary ships, surface habitats, fuel factories, return vehicles, radiation shielding, life support. Every piece must connect with every other piece. If one fails, everything stops. And yet, despite all these obstacles, people continue planning this journey. Scientists dream about it. Engineers design machines for it. Private companies invest billions to attempt it. One famous company leading that effort is SpaceX. Their massive rocket, called Starship, is designed specifically for deep space transportation. Unlike older rockets, it aims to be fully reusable, flying again and again, reducing cost dramatically. The plan is ambitious. Launch enormous cargo ships toward Mars, deliver habitats, power systems, fuel production plants, then later send humans. A fleet of spacecraft arriving together, building a small settlement, at first only temporary, later perhaps permanent. If successful, humanity becomes a multi-planet species, not confined to one world. But notice something important. None of this violates physics, no mysterious technology required, no exotic energy sources. Everything relies on known science, chemical rockets, orbital mechanics, thermodynamics, the same physics that guided the moon landings. The difference is scale. Mars demands much more engineering discipline, much greater precision, and enormous patience. The moon mission was heroic, but it lasted days. Mars missions span years, entire careers of engineers, and possibly entire lifetimes of astronauts. Which brings us to a final thought. The rocket equation does not forbid human travel to Mars, but it does something else. It filters bad ideas. Any design that wastes mass quickly fails. Any mission that ignores physics collapses under numbers. Only the most efficient, carefully planned solutions survive. This is how nature works, not through opinions, but through equations. And those equations quietly decide what humanity can achieve among the planets. One day, humans may stand on Mars, just as they once stood on the Moon, looking upward at a distant blue planet, realizing something extraordinary, that reaching another world was never about distance. It was about understanding the rules of the universe and learning how to live within them.